Atoms are the tiny building blocks of everything we see and feel. This energy, locked deep within the atom's core, is the driving force behind both nuclear fission and fusion. Fission is like snipping a tightly wound spring, releasing energy as it unwinds chaotically. Fusion, on the other hand, is like combining two springs, creating an even more powerful, coiled entity. Both processes release enormous amounts of energy, dwarfing even the most powerful chemical reactions. The quest to harness this atomic power has driven scientific innovation for decades. Understanding the balance between these two sides of the atomic coin is crucial as we navigate the future of energy production. Nuclear fission, the process of splitting an atom's nucleus, is the engine behind our current nuclear power plants. Imagine a neutron hurtling toward a uranium atom's nucleus, pushing it over the edge. The result is a chaotic splitting of the atom, releasing energy and more neutrons. These neutrons strike other uranium atoms, creating a chain reaction. This chain reaction, the heart of a nuclear reactor, is carefully controlled to release energy at a steady rate. The heat generated is used to boil water, creating steam that spins turbines and generates electricity. However, the efficiency of fission comes with a catch radioactive waste that remains hazardous for thousands of years. Despite these challenges, nuclear fission provides a reliable, carbon-free source of electricity, helping to combat climate change. Ongoing research and development of safer, more efficient reactor designs offer hope for the future. If fission is the splitting of an atomic spring, fusion is the art of combining them. This process, powering our sun, involves fusing two light atomic nuclei into a heavier nucleus, releasing immense energy. It's the holy grail of energy production, promising clean, safe, and nearly limitless power. Imagine two hydrogen nuclei smashing together with incredible force, creating a helium nucleus and releasing energy. Replicating this process on Earth is a monumental challenge, requiring extreme temperatures and pressures. Scientists use powerful magnets and lasers to confine and compress hydrogen isotopes into a superheated plasma. While achieving sustained fusion energy remains a work in progress, the potential rewards are enormous. Fusion power plants would be inherently safer than fission, with minimal radioactive waste. The realization of practical fusion power would be a paradigm shift, paving the way for a cleaner, more sustainable future. Understanding the concept of half-life is crucial when discussing the dangers of nuclear energy. Radioactive isotopes decay over time, emitting radiation as they transform into more stable elements. Half-life is the time it takes for half of a given amount of a radioactive isotope to decay. For example, iodine-131, used in medical imaging, has a half-life of about 8 days. This means that after 8 days, half of the initial amount will have decayed into a more stable form. The half-lives of radioactive isotopes vary greatly, from fractions of a second to billions of years. This has important implications for nuclear waste management, requiring long-term storage solutions. The challenge lies in safely containing and managing these materials to prevent harm to humans and the environment. The concept of half-life is also crucial for understanding the dating of ancient artifacts and geological formations. Nuclear energy, like any powerful tool, possesses both immense benefits and inherent risks. On the one hand, nuclear energy offers a compelling solution to some of our most pressing energy challenges. Nuclear power plants do not emit greenhouse gases during operation, making them valuable in the fight against climate change. They are highly efficient, producing more energy from a smaller amount of fuel compared to traditional power plants. However, the risks associated with nuclear energy are significant and cannot be ignored. Accidents at nuclear power plants can have catastrophic consequences, as evidenced by Chernobyl and Fukushima. The disposal of radioactive waste presents a major challenge, requiring careful management and secure storage for thousands of years. The potential for nuclear weapons proliferation is another serious concern, posing a threat to global security. As we navigate the complexities of the 21st century, the question of how to power our world becomes increasingly urgent. Nuclear energy, with its immense power and inherent risks, stands as a complex and controversial option. The allure of clean, efficient energy is undeniable, especially as we grapple with the urgent need to reduce our carbon footprint. Yet the spectre of nuclear accidents and the long-term challenges of waste disposal serve as stark reminders of the potential consequences. The future of nuclear energy hinges on our ability to innovate and develop safer reactor designs. It also depends on our commitment to international cooperation, ensuring responsible use of nuclear technology. The decisions we make today will shape the course of our energy future and determine the legacy we leave behind.